So welcome back. We got this Ampere's law situation. Ampere's law is really important, and what it basically says is, look, you know, as we talked about earlier. So is my current carrying wire, let's say the current's coming towards me, I'm looking down from above, and I have these loops of magnetism, and because it's coming towards me, I know that these loops are going to go in a counterclockwise direction. And it's like a concentric rings. I said before it was like a Swiss roll, and that's misleading actually. It's not like a Swiss roll. Swiss roll is like a roly-poly thing where you roll something up. This is not a whirl. This is concentric rings. Pardon? Like an onion, yeah, that's actually a good analogy, yes. That's like an onion. And so, and what do we know about the magnetic field strength as you go away from the wire? What does your intuition tell you? Is it going to get stronger, stay the same, or get weaker? It's going to get weaker. So as this thing gets weaker, the length of these circles gets longer. So when something's decreasing as something's increasing, there's always this temptation to say, I wonder if their product is a constant, you know? One thing increases, the other thing decreases. If you think about it, you could think about that with inverse square law, where you say, yeah, the intensity is getting less, but the surface area of the sphere is getting more. And so, you know, there's some consistency there. There's this thing in terms of gravity or electrostatics is called the field, which is, you know, as it spreads out over a different volume, spreads out over a different surface area, but it's passing through all points. Well, this is a field as well. This is a magnetic field. It's not a spherically symmetrical field, though. It's a radially symmetrical field, yeah? So, okay, because it's a long wire. So it's like if I imagine, if there's my wire, it kind of spreads out like that and like that. So it's cylindrically symmetrical. So we say, consider magnetic field around a long straight current carrying wire. As we move further away from the wire, B decreases, but the circumference of the circle that B is represented by increases. Is something conserved? And what we find out, and this is Ampere's law, the line integral B dot S ds around any closed path equals mu naught times I. Permeability of free space times the current, where I is the total continuous current passing through any surface bound by the closed path. So this is what's going through my wire. So I practice, you know, the line integral B dot ds is equal to mu naught times I, and I'd like you to know that, please. And let's use it. So, and again, I'm sorry, I did this thing before where, you know, I did it and then we'll talk about it. So example, an infinitely long current carrying wire follows the positive y-axis. So here's my current carrying wire going in the y-axis. Using the method of Ampere's law as shown in class, show that B is equal to mu naught I over 4 pi over 2 pi r at a point that is r meters from the wire. So here's my point of interest. And we say, well, the integral, surface integral, sorry, the line integral of B dot ds is equal to mu naught times I. That's my Ampere's law. And so I say, well, hold on. B, that magnetic field vector, is going to be tangential. And that's going to be parallel to ds, isn't it? They're both tangential. So they're parallel to each other. Okay, so that is parallel to that. And that means that, oh, the angle doesn't matter, because when they're parallel, it's the cosine of 0, which is 1. Yeah? That's what we want for a, remember, for a dot product, A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So when these two guys are parallel to each other, that's great because I don't need to worry about the angle between them anymore. And B is constant, on the loop, but equal distance away. So that means this imaginary loop, imaginary like my Gaussian surface was imaginary. So this is an imaginary loop. It's not a loop of wire. We just did Boyer-Savart where we had loops of wire. This is not a loop of wire. This is an imaginary loop. So, but it's constant distance away from the vertical wire, so that means that B is constant. So I can take B outside the integral. So B, the integral ds is equal to mu naught I. And what is the integral ds? Well, it's just the circumference. It's all these ds's added up, which is 2 pi r. So B times 2 pi r is equal to mu naught times I. So we get B is equal to mu naught I over 2 pi r. Yeah. So B dot ds, mu naught I, line integral. We let the thing play out. Okay. So using the method of Zampo's law as shown in class, determine the magnitude of the magnetic field at 0.7 meters from an infinitely long wire that carries a current of 5 amps. So here's my wire, and I have 5 amps, and I'm at this point which is 7 meters away. There's my point of interest. So there's that, and the rest is up to me. So we're going to harken back to some of our previous approaches. And the first thing, sorry, no, I need to change my color. Let's go to a red. So the first thing I want to do, if you remember when we did Boyer-Savart, we wrote down Boyer-Savart. So let's write down Ampere's law. What was Ampere's law? The line integral of, what is it? B dotted with ds. And I make my dot really big. People sometimes put a dot down, and sometimes it's there, sometimes it's not there. Is equal to, what was the next bit? Mu naught times I? Okay. So now I do my imaginary bit. I want to pick a line which has a lot of symmetry, but goes through the point of interest, just like we did in Gauss's law, using that same strategy. So I say, oh, I'm going to take a circular loop, y, because r is constant, and ds is parallel to b, which is kind of nice. So I say, okay, I'm going to say b is parallel to ds, so b dot ds equals b ds cosine theta, and that equals 1, which equals b ds. That's kind of nice. And I can say, oh, b is constant, so I get b line integral ds is equal to mu naught times I. I can say the line integral of ds is equal to, in this case, circumference, which equals 2 pi times r. So b is equal to, b times 2 pi times r is equal to mu naught times I. So b is equal to mu naught I over 2 pi r. Then b is equal to mu naught. What was my I? 5 amps. 2 pi. What was my r? 7 meters. Which equals 5 over 14 pi mu naught. And what would the units be for magnetic field? Tesla. So in principle, I could have used Boyer-Savart to do a question like this. But it would have been hard because the angles would be changing. As I had different bits of ds, my angle would have been changing to my point of interest. So it would have been, a bit of a bear. This is an alternate way, which works great for this case. So when it's a part of a circle, I'm going to use Boyer-Savart. When it's a bit like this, I'm going to use Ampere's law. I'd like you to know Boyer-Savart's law. I'd like you to know Ampere's law. I'd like you to be able to use the two of them. Okay? Let's use Ampere's law in, again, a more involved circumstance. This is a helical coil. Thursday's lab is going to be based on this. It's a slinky. Current flows through. It forms effectively a bar magnet. One end will be north and one end will be south. And I can actually tell you, I'll tell you now how I know which way around it is. If you look down the slinky, if the current is going in a counterclockwise direction, you are looking at north. And if you're looking in a clockwise direction, it's a south. Can you see how, I'm talking about my current I and my current I. Can you see how that works? I take the letter and just make it curly, and then I put arrowheads on the end of the letters, and it tells me which way around it goes. Okay, so I'm going to make a magnet, and I'd like to know the magnetic field inside, actually. I'd like to know how strong is this magnetic field inside for a given current and a given set of dimensions for the device. And so what I say is, using the method of Ampere's law, as shown in class, show that B inside the solenoid is B equals mu naught N over L. N is the number of loops, and L is the length of the solenoid. Okay. So as long as I have my imaginary Ampere's loop pass through the middle of the solenoid, I can get an answer. So I choose to have a rectangular loop. It's going to have 4 bits to it. Didn't we do something like this for the torque on a coil? Yeah. 1, 2, 3, 4. What we can say is that on this top loop, let's first of all recall Ampere's law. So recall Ampere's law, this line integral of B dot ds is equal to mu naught I. So strategically, I'm going to pick bits where basically there's no current if I can in my bit, or maybe my B is parallel to my ds, or my B is perpendicular to my ds. If they're perpendicular to my ds, it's the cosine of 90, which is 0. So if I look here, I have my ds, and think about my B. My B on all those bits of wire, okay? And all those bits of wire, I'm so sorry. Let me have a look at this. So my B, yes, my B is going to be up through here. Effectively, I've got B's on the inside, and I've got, because these go big, large arcs, no B's on the outside. Okay. So on this piece of wire here, what I say is for inside one, for side one, I'm sorry, for side one, I say B, which is upwards, or 0, whichever one you like, is perpendicular to ds. If it's perpendicular to ds, b dot ds equals 0. And on this bit, same thing. So for side 3, that equals 0. For side 2 is way out here. Effectively, the magnetic field is so weak out there, we can say B equals 0. It's a bit of a stretch, but we can say side B equals 0, so that goes to 0. So out of all of these, the only one I'm really interested in is this side here in the middle. Let's clean this up a bit so we can see it. So let's focus on that bit. I'm going to change colour pen so that it's not so, let's go to purple. So I'm interested, let's go to purple. So I'm interested in this side here. And what I say is, for side 4, the line integral of b dot ds is equal to mu naught times I. B is constant inside. That's one of the features of it. So I can take b outside my integral, and I get b times the line integral ds is equal to mu naught times I. The line integral ds is just that length there, what I'm calling L prime. So the line integral ds equals L prime. So b times L prime is equal to mu naught times I. Okay. My current is equal to I times my length, the number of turns inside. Okay. Remember, Ampere's law refers to the number, the amount of current flowing through my loop. Well, there's I there, but then there's I there, and then there's I there. I'm choosing to loop this wire round and round. So the current flowing through my loop is not I, it is I times the number of turns inside my loop, which I'm calling N. So I is N primed. I is equal to the number of turns inside times I. So that's my total current. So B times the length of my loop is equal to mu naught times I times the number of turns inside my loop. Now, I wasn't given either one of those. I was given the number of turns in the coil and the length of the coil. But if it's a uniform coil, then the number of turns inside my loop divided by the length of the loop is equal to the number of turns inside my entire solenoid divided by the length of the solenoid. Put that there. So B is equal to mu naught, and rather than saying I times N dash over L dash, I go mu naught I N over L, where N is the number of turns in my solenoid and L is the length of my solenoid. Okay? So it's kind of interesting. We use solenoids a lot, and we just pull the equation out, and this is where that equation comes from. Okay? I don't expect you to be able to do that on a test, just like. Okay? But I do expect you to be able to do it now. So how we do? Just let me have a look and see how we're doing for time. Yeah. So let's just go through that again, step by step. So we're going to say a solenoid consists of a wire helix. Let's just make it like that. And it has a radius of 3 meters. So, and the helix is 6 meters long. And n equals 10 loops. I equals 8 amps. Flows through it using appropriate. Oh, cheat. Okay, well, we'll do that to begin with. Using the appropriate equation. What is the magnitude of the? Oh, happy day. Thank you, Dr. B. That's great. B is equal to mu naught. What was it? N over L times I, which equals mu naught N 10 over L 6 times I 8. So that equals mu naught 80 over 6, which equals 13.33 mu naught Tesla. Oh, so that's not bad. So know the equation. Yeah. Okay. Because that can be nice. But let's do it the other way as well. Okay. Agreed? I'm going to give you a second to copy that down and then we'll come back and we'll just reinforce what we did before. So can I erase? Let me know when. Let me know. Can I? I can see a couple of people are still writing. But okay. It's gone. So, like we've done in the past, write down Ampere's law. What's Ampere's law again? B dot ds integral is equal to mu naught times I. And there's a funny symbol on this bit. What's that? That just symbolizes going around the loop, whatever that is. Okay, so I need to create for myself a loop. So remember, this is made up. This is me making this up. And I am going to choose all the symmetries I can get. So I'm going to make up a symmetry like this. And I'm going to have 4 sides to it. 1, 2, 3, and 4. So for 1, the significant thing is that the B vector, which is vertically upwards, let me change my colour pen to put the B vector in. B vector, B. And let me have a little bit of ds, just so I see it. So for 1, B dot ds, B is perpendicular to ds, yes? So that means that B dot ds is going to be the cosine of 90, which equals 0. Yep. And for 2, sorry, I changed my numbering scheme. B is perpendicular to ds. So B dot ds is equal to 0. And let me come back down here. follow that, and there's my ds, if you like, there, to kind of show my B and ds are perpendicular. For 3, B equals 0. I'm out here somewhere, and the magnetic field is concentrated inside, but not on the outside. Does that make sense? So B equals 0. So B dot ds is equal to 0. So that leaves me with 4. So for 4, I got to do it. Okay. B is constant. Let's have a look. B is parallel to ds. So I can say that B times the integral of ds is equal to mu naught times I. So which gives me that B times L dash, let's call that L dash, is equal to mu naught times I. And okay, B times L dash is equal to mu naught. It's really, isn't it? It's actually I dash. It's the amount of current flowing through here. I dash. And I can say I dash equals N times N dash times I. And these are N dash things inside there. So this BL dash equals mu naught times I dash, which equals N dash times I. So B is equal to mu naught N dash over L dash times I. And then N dash over L dash equals N over L. So B is equal to mu naught N over L times I, which equals mu naught N, 10 loops, over L, 3 meters. There you see, Bonner. I should be looking here, shouldn't I? I went to all the trouble of doing this diagram, then I'm blowing it away by looking up here. That's me making a mistake. It's over 6 times I. And I is, did I put I down? Yes. See? The system works. AD over 6. Didn't we just work this out? Yeah. What was it? 13.0. AD over 6 is 13.33 mu naught. And that would be in Teslas. So not bad. I like it because it's got some echoes of Gauss's law in there. It's kind of like I'm strategizing about what shape to pick and, you know, etc. Notice, please, you know, supposing I told you that the solenoid had 6 loops per meter. I've given you the N over L. So don't get fooled, you know. If you're expecting the B equals mu naught, big N over L times I, and I don't tell you the big N and I don't tell you the L, I tell you effectively the little n. This is usually defined as little n. then, you know, don't get fooled by that. Don't get put off because of different N, you know. Be mindful of what the symbols mean. And be mindful of what I can, as a teacher, can do just to make it that a bit more interesting, okay? I want to do one more thing. I want to go back. I skipped a slide. I want to go back, way back here. Let's look at some symmetries here, similarities. This is electric field and this is magnetic field. And don't they look somewhat similar? You know, we have an inverse square, and we have some kind of integral, and we have some kind of integral, and then we have some constant, we have some glorified constant, well, with an I in there, it's not exactly constant. So I can see how, you know, all right, I can see they're kind of somewhat similar. But, you know, here's a point source of charge, and here's my electric field lines radially going away. And this is my current carrying wire, and here's my field lines, and they are symmetrical about them in a circle. And they're tangential to that circle. So you a certain distance out, and then you're tangential. Certain distance out, and then you're radial. And there's different math associated with these things. This is diverging, and this is curling. So you guys have you done divs, grads, and curls yet? No? Divergence?
Yeah.
Okay, so that's where that math comes in. Okay, so, okay. Similarities and differences. Let's cut through and do this bit. And similarities and differences. So before we had the idea of electric flux, and that equaled, what did electric flux equal? Integral of E dot dA? A was a made-up vector, wasn't it? It was this little area vector. It worked. Let's do the same skill. Magnetic flux is equal to the integral of B dot dA. Okay, so there's my equivalent. The unit magnetic flux is in, well, it's going to be Teslas per square, Tesla square meters, and that's sometimes called the Weber or Weber. Weber, it's German. And because magnetic field lines are closed loops, that old question which I asked you on the last test about, you know, here's a whole bunch of charges and what's the flux through here? Because there was a beginning and an end to the flux, yeah? The lines ended on negative charges and began on positive charges. These guys, magnetic lines don't begin and end, they're just loops. So by definition, no matter which magnetic field lines I choose to draw for everyone coming in, it must leave because there's no beginning and end to them. So almost by definition, my magnetic flux is equal to 0 in a closed surface. Okay? So we said, good old Gauss's law, area integral of E dot dA. This was before I made my dots big. Equals Q in over epsilon naught. My magnetic flux is equal to the integral of B dot dA, which equals 0. We're not going to do that same pattern of questions. You know, they had like 4 or 5 different Gauss's law scenarios for electrostatics. You know, you had the ball of charge, inside the ball of charge, outside the ball of charge, inside the shell of charge, outside the shell of charge, near the wall of charge, near the wire of charge. We're not going to do the same thing on this because the answer is always 0. So it's kind of like, you know, and the answer is 0. So there's similarities between them. Except we have an interesting situation with regard to capacitors. And I'm going to be honest with you on this. I'm going to just point you in this direction. This is Useful for developing Maxwell's equations. And basically, I just want you to know that Maxwell's equations exist. We've used a couple of them, but the other two we won't particularly use. We'll just point you towards them. You'll do a lot of them if you continue with either modern physics or you do anything to do with electricity when you go on to the next level. But there's a kind of issue in that when I have a capacitor, no charge actually flows through the middle of the capacitor. And so if I imagine a capacitor charging up, I can say, well, hold on, current did flow through that bit of wire, but current didn't flow through that bit of wire, that bit of space. So if I happen to draw a Gaussian, if I had to put my ring here, my loop there, then there was a current flowing through it. But if I kind of curved my loop or put my loop in the middle, there'd be no current flowing through it, and yet it's the same device under the same circumstances. And so there's a bit of an issue. We say, remember that Ampere's law says that the line integral of B dot ds equals mu naught to I. Consider path P, and path P is this ring here. S1, so surface 1, that's the surface on that plane there. Surface 1 has a current I flowing through it. S2 does not have a current flowing through it. So we have a bit of a conflict because we said, well, for the surface, you know, the current is the current flowing through the surface. No one said it had to be flat. But if I take a flat surface, then I do have a current. If I take a curved surface, I don't have a current. So this breaks down. So the answer is, we pretend there's a current flowing through the gap. We say, we define a displacement current. The displacement current is considered as flowing through the capacitor's gap. So we kind of cheat. We say the displacement current is equal to epsilon naught d phi e by dt. And so now we can shove that in and we say we get Ampere Maxwell's law, which is the integral of B dot ds is equal to mu naught, and we say I plus the displacement current. And so we get the line integral of B dot ds is equal to mu naught I plus, and we substitute in and we get mu naught epsilon naught dE by dt. We take that bit and we substitute into there. And I don't do anything with it, to be honest. Okay, so, you know, we end it there. I'd like you to know that the displacement current exists. I'd like you to be able to recognize this as one of Maxwell's equations, but I'm more interested in you knowing Ampere's law and being able to use that. Okay? Cool. So let's end it there.